announcement about a new mathematical journal that is arranged jointly by the IMS Stony Brook and Springer. The journal title is the Ireland Mathematical Journal.
Do I have 60 minutes?
Yeah.
60?
And so there's a big clock.
Yeah, I see the clock. Just making sure.
And I have left some posters and cards with the information about the journal in the common room. You can pick it up there, and we invite contributions of any kind. This is a very general journal, so the only thing is that we want the papers be understandable, which is quite natural. What special features that we welcome problem contributions, well-motivated well-motivated statements of problems, new or maybe repeated statements, but the new motivations are also welcome. Please submit your papers and let know your colleagues. I believe there will be no formal proceedings for the conference. Instead of proceedings, please submit. Please submit to the Ireland Journal. Thank you.
Okay. Okay, so our next talk is Barak Weiss from Tel Aviv, also via Stony Brook some time ago. So you'll tell us what you're going to say.
Okay, thank you very much. It's a great honor to be invited to speak here. So I was a postdoc here around 17 or 16 or for 2 years, from 1998 to 2000. And a lot of what I'm going to talk about started back then. And specifically, it's a mix of two topics, which are homogeneous dynamics. That's actions on homogeneous spaces of Lie groups. And spaces of translation surfaces, or you might call them holomorphic one-forms over Riemann surfaces. And so I came here with a background in homogeneous dynamics, and I picked up everything starting here about translation surfaces. So it was a great time. It's great to be here. Let me mention my co-authors to the work that I'm describing today. So this is joint work with John Smillie and Matt Bainbridge, which I'll get to in the second half of the talk. And so I'm going to start off kind of telling you give you a broad picture of what the topic is, because it might not be a topic that many of you have considered before. I'll tell you what we're studying and why. And in the second half of the talk, I'll tell you more about what we've recently been able to do. So what is a translation surface? So I'll be just showing pictures on this on the screen, but I'll be writing. And please tell me if my handwriting is too small. So let me define a translation surface. So a translation surface is a finite collection of polygons which are glued along pairs of edges. And the edges have to have equal length and have to be parallel. And everything is considered up to an equivalence relation, which I'll call cut, translate, and reglue. So this is not a very precise definition, but let me still explain what I'm talking about. So the screen is not showing us the picture anymore. Should I just wait? What am I? Oh, here we go. So here's an example of a translation surface. So actually, you're seeing the same translation surface presented in two different ways. So I can't really. Okay. So on the left is one presentation. If you can see my mouse moving around, this is an edge of a polygon. And actually, there's one polygon on the left-hand presentation, one of its edges, namely this vertical edge, is identified with this vertical edge. I'm not showing you, oh, it's gone again. Okay, here we go. I must have, oops. What am I doing wrong? Okay, so what I wrote is that we're taking a finite unit of polygons, and these polygons have edges, and all the edges, all the edges are paired up in pairs of edges which are parallel and of equal length. And so I won't touch the computer just because it's not liking that. But what you're seeing here, this vertical edge and this vertical edge are parallel and of equal length, so I just consider them to be identified with each other. And similarly, there's a diagonal edge. You can take a look yourself, and you'll see that all edges have partner edges of equal length and parallel, and we consider them to be identified. One such object is called the translation surface, and there's an equivalence relation. The equivalence relation makes these two pictures equivalent to each other, and the equivalence relation is that you're allowed to take a polygon, chop it up into smaller polygons, and translate those polygons around. Only translations are allowed. Rotations or other maps are not allowed. Reflections are not allowed. And you get a different presentation of the same surface. So you can amuse yourself by looking for every, this triangle you can find somewhere else in that picture. And all the little pieces on the right-hand side should all also exist on the left-hand side. And more importantly, the gluing rule should be the same gluing rule on both sides. Okay, so those are two different presentations of a translation surface. Now, this looks like a completely combinatorial object, but it comes from complex analysis. So equivalently, this is nothing else than a pair. It's a pair consisting of a Riemann surface, X, and a holomorphic one form. So I won't go into why those 2 points of view are equivalent. Basically, these objects that you're seeing are topological surfaces, and you can use the flat structure that you get from these pictures to put a Riemann surface structure on these pieces. It's going to be everywhere flat except for a finite set of points where the structure has singularities. And you can make a Riemann surface out of that, and then the DZ one form on the plane can be pulled back and to give you a holomorphic one form, which is holomorphic with respect to this Riemann surface structure. Now, there are these special points that I told you about. I'm debating whether I should touch the screen now just to make it more visible. So let's try again. So I want to show you, you're seeing that in these pictures there's a black dot in several places and a dot that's not blacked in. So this is a black dot. It's a vertex of a polygon. Now, if I start running around it and following the identifications, I'm going to move clockwise around it. So I've picked up 90 degrees of angle here, and then the identification pushes me over here, and I get 90 more degrees of angle over here, and then 180 over here, and then I don't know how many over here, and so on. And if I keep going like that, I'll end up where I started. And because all the jumps that I did were by translations, the notion of angle is well defined. So I'll be going through some multiple of full circles, so some multiple of 2 pi, some integer multiple of 2 pi, but it's not going to be 2 pi. So in this case, there are two such points, the blacked in one and the one that's not blacked in, and each of them has a cone angle of 4 pi. And we have a notation for that. The notation is in the language of holomorphic one forms. The one form has 2 zeros. These points are zeros of the one form, and the orders of the zeros are 1 and 1. And so our notation for such creatures is H11, or more generally, if we had k zeros of orders A1 through AK, we would denote that as an element of H of A1 through AK. So H A1 through AK is the space of translation surfaces with k singular points of cone angle 2 pi times AI plus 1. So a regular point in the plane has cone angle 2 pi, and these AIs are telling you the excess angle, the excess number of times you go around 2 pi around those points. So that's so what I've defined for you an object, which is a translation surface. I've also defined for you a space, which is the space of all translation surfaces of a particular type. And another thing that I should also define when looking at these translation surfaces, there are preferred interesting lines which are called saddle connections. And these are straight lines running through the translation surface connecting singular points. So if you look at the cursor again, there's a line going this way, a horizontal line from this point to this point. So that's a horizontal saddle connection. But of course, there are much more complicated saddle connections that run through the picture multiple times. I could start off here, jump over here by the identification, jump over here by the identification, almost at this point, keep going, and whatever. Eventually, after a long, long time, this could close up in a straight line, and I get a saddle connection. So these guys have saddle connections on them, which will come up again and again and again. Okay, so we've defined a translation. We've defined the space of translation surfaces, and there's going to be an action, and the action is an action of linear transformations. So if so let's denote the group of 2 by 2 invertible linear transformations by G. Invertible linear transformations of R2 by G. So these are linear maps of the plane. They act on the plane. Therefore, they act on polygons. Since they're acting on polygons, they act on these pictures. They preserve the equivalence relation. So they act on these spaces. So this acts on a stratum of translation surfaces via linear transformations. Acting on the plane. And we're going to be interested in the ergodic theory of this action. So let's show you a picture of what that looks like before giving more details. So we take another translation surface, the one on the left here, and we apply a linear map to the picture. The linear map is a Horocycle, is a unipotent linear map, so it's preserving the horizontal direction and shearing everything. Shearing the higher up you go, the more you shear to your right, and it's transforming the left-hand translation surface to the one you see on the right-hand side. So that's the action that we want to study. And on the face of it, when you see this for the first time, you might think that this is a very boring action. I've shown you the action of a matrix which is not very big. It hasn't deformed the surface by too much. But you might think that if I had a large matrix, so a large matrix of this group is going to have a large contracting eigenvalue and a large expanding eigenvalue and a small contracting eigenvalue. So it would maybe take a polygon, say this was a polygon, and you apply the map and you get it, very, very stretched in some direction and looking completely degenerate. And you might think, well, what a boring dynamics to study. All the polygons just get stretched and become unrecognizable. That's true of the action on the space of polygons, but it's not true of the action of the space of translation surfaces because we have an equivalence relation. So we can now take such a deformed translation surface and cut it up into pieces and rearrange, and we might get the same thing we started with, or we might get a very different picture. Okay? So I haven't defined a metric, in fact, and there is no, well, I should say there are few natural metrics people might put on this space and study, but I haven't defined a metric on this space, but what I will define is a topology. So you want to make this into a space with structure to start working, and we put a topology on it by, I'll just define it, I won't define it, I'll explain it loosely. So what is a neighborhood of a of a translation surface in this stratum, well, you present your translation surface as a union of polygons, and then you're allowed to wiggle the vertices of these polygons by a small deformation in the plane, but you're only allowed to wiggle them in such a way that edges that used to be parallel of equal length are still parallel and of equal length. And so, in other words, if I want, I can wiggle this vertex by, say, moving it up, but then this edge has become longer. So I need to, when I wiggle these two vertices, I should make sure to make the edge longer and have the two edges parallel and of equal length, so I can still attach them. So I make small wiggles locally in one of these presentations. It's something you verify that it doesn't really depend on the presentation, and you get a topology. And with this topology, the stratum becomes an orbifold. And in fact, this orbifold carries a nice finite measure. So to make that completely precise, we need to restrict ourselves to area 1 translation surfaces. We can measure the area of a translation surface. We restrict to translation surfaces of area 1. On this space, there's a nice finite invariant measure of full support for this action. And in the 80s, people started studying this as a dynamical system. And a well-known theorem of Howey-Maser from the 80s is that this is an ergodic action. So let me write that down. In particular, so let's let U be the group of upper triangular unipotent matrices, which will play a major role in this talk. So these are the matrices that I've shown you on this picture, and this is called the Horocycle flow. So Maser also proved, or it's just kind of a immediate corollary of when you have an action of GL2R, which is ergodic, its restriction to this group will also be ergodic. So this is an ergodic action, and in particular, almost every orbit in this space is dense. So again, what that means is if I take a random translation surface, which means I take this initial guy and I perturb it by an arbitrarily small amount, almost every perturbation, and then I start applying this map that stretches it, shears it in the horizontal direction, and I rearrange polygons, I'm going to see all possible shapes of translation surfaces up to smaller and smaller errors in this way. Okay? So this is indeed a complicated enriched dynamics. Now, motivated by things that people did in homogeneous dynamics, specifically Ratner's theorem, which is a theorem that I'm not going to go into, but for those of you who know it, it's a classification, complete classification of all invariant measures in all orbit closures in a particular particular dynamical systems of algebraic origin. So motivated by that, people started asking, is it possible to understand and classify all the invariant measures and lead to an understanding of the behavior of all orbits? So we want to replace this almost every with an every. Now, it's not going to be true that every orbit is dense. What you want to say is that if you look at a translation surface, there's a way to figure out what its orbit closure is going to be, and these orbit closures have some kind of nice classification, reasonable classification. So, if you're used to hyperbolic dynamical systems, it's always the case that you have orbits which are fractal, and there's uncountably many orbit closures, and sort of no hope of writing down a list of the possible orbit closures. But in this dynamical system, the hope was, and still is, that one can do this and get a complete classification of orbit closures. And now comes these amazing bits of work by McMullen for genus 2 and Eskin, Mirzakhani, Mohammadi in arbitrary genus. So let me just write that down without being too precise. 2005, if I remember correctly, and Eskin, Mirzakhani, Mohammadi, and this is recent, so this is all genera, and it's has not appeared yet, so to appear. And what they are able to do is classify all the GL2R all the G-invariant measures and orbit closures and classify is a big word, so let me put quotation marks around this. So in the homogeneous space situation where this is, which is inspiring this kind of a work, there is an honest classification in the following sense. If I give you a particular space, one of these spaces, which in our analogy would be one of these strata, one can come up with a list, a countable list usually, of families of measures and possible orbit closures. And this list is given in terms of data coming from the theory of algebraic groups. So there's you have to open a book on algebraic groups, study the book on algebraic groups, and that tells you what the possibilities are. But that's the way the classification works. In this theory, it's not yet a classification, but hopefully we're moving ahead towards a real classification. Right now, what Eskin, Mirzakhani, and Mohammadi tell us is that these orbit closures and these invariant measures are very, very restricted. They come from certain constructions which have to do with algebraic geometry and have to do with flat structures on these moduli spaces. And they're very, very restricted. There are only countably many of them. They're associated with lots of algebraic data, like totally real algebraic number fields, and so on and so forth. So this is a very big development. And lots of ongoing work is involved in fleshing it out and making this into a real classification. So what I want to do in the next few minutes is sort of explain why this is so useful beyond the fact that, that Ratner could prove it in homogeneous dynamics, and now Eskin, Mirzakhani, Mohammadi can prove it in translation surfaces. You might not be too impressed by that. So let me give you some applications which are very simple-minded in a sense, but they just show you the power of this theorem. So the applications that I want to present are in the field of billiards, rational billiards. So what's the relevance of billiards here? So if you have a polygon in the plane, you can play billiards on it, which means, let's draw a silly picture over here. So billiards and polygons. You have some kind of a polygon in space, in the plane, and then you imagine the dynamical system that is the tangent bundle to this polygon, and you just move along straight lines, and whenever you hit the wall, you bounce off so that the angle of the exiting angle is equal to the entering angle, the usual laws of reflection, and that defines for you a dynamical system. The behavior at the vertices is not defined, so you remove those from your phase space, and that's a well-studied model for dynamics with lots and lots of mysteries in it and lots of open questions. And so what you do to relate this question of billiards and polygons to translation surfaces is what's known as the unfolding construction. So I've illustrated this here by starting with a triangle. It's this particular right triangle with these angles that you're seeing, say, on the bottom of the picture. And then whenever your billiard trajectory hits a wall, instead of reflecting the billiard trajectory, you reflect the polygon around that edge. And that's called the unfolding procedure. So all of the triangles that you're seeing in this picture are the same triangle reflected across its edges, and the straight line path starting here is the unfolding of a billiard trajectory, and now it becomes a straight line. Now, if we do this in a general polygon, we get infinitely many reflected copies of this polygon. If the polygon that we started with had rational angles, which means angles which are rational multiples of pi, this group of reflections that we use is a finite group. And so after some number of times, we're going to get two polygons which are translates of each other, because we'll have reflected by the linear part of the group element will be trivial. It'll just be a translation. And then instead of adding a new translated copy, we just identify those two copies along edges. And so I don't know if in this picture we have gotten that far. I guess not. So this is a full set. If this trajectory were to go backward and exit it through this wall, instead of reflecting and getting a new polygon over here, we could use the polygon that's next to the top one over there. And so all the polygons, you get finitely many polygons. They're all glued to each other along edges. All the edges are glued to parallel edges. We get a translation surface. So this billiards in that triangle gives rise to this translation surface, which looks like an octagon, a regular octagon. These two things are actually the same, two presentations of the same translation surface. And we've transformed the straight line flow, the billiard flow, into a straight line flow. Okay, let me tell you two problems that have been around for a while about billiards, and they can be solved or at least attacked using this strategy. So the first is the so-called illumination problem. So the illumination problem is a kind of a fascinating, silly little problem that's been really annoying and been around for a long time. So in the 50s, someone asked whether it was, someone called Strauss asked, someone who had a name, but I know nothing other than about him, asked whether it was possible to find a polygon with 2 points in it that could not be connected by a billiard path. So if you're thinking of this polygon being a hall of mirrors, you can't shine your laser beam from one point and have it reflect off the sides and hit the other point. And the example was given in the 90s by Tokarsky. So this is the first example showing that you could actually have 2 points which do not illuminate each other in a polygon. If you shine a light from A, and you're never going to hit B. If you try to, I'm reminding you that billiard paths are not defined when they hit these vertices. So if you want to go horizontally across, you hit this vertex. If you want to reflect once, you're going to have to reflect over here, but this happens to also be a vertex. You might want to sort of reflect 4 times like that, but then you have a vertex over here and a vertex over here. So this picture is arranged in such a way that Tokarsky proved that one could never make it from point A to point B by a billiard path. And lots of variants of this, of related problems, have been proposed, and they're still open. And recently, using this Eskin, Mirzakhani, Mohammadi result, we've been able to prove it's fairly, it's a fairly direct application. So consequences. If P is a rational polygon, consequences of this. So I'll call the Eskin, Mirzakhani, Mohammadi theorem, I'll just refer to it as EMM. So if P is a rational polygon, and X is a point in P, then the set of Y's such that there's no billiard path from X to Y, this set is finite. So these examples do exist, but they only, for every given X or A in that picture, there are only most finitely many B's with that property in that picture. And there's lots of additional questions one might ask about this, which are still open, still being studied. The rationality here, you might want to remove this assumption. We definitely need this assumption because everything that we do relies on this EMM paper, so we have to use this unfolding process that I described, and that only works for rational polygons. You could ask about how many pairs there might be on a translation surface and what they might look like. You could ask whether if you have blocking, in other words, if 2 points do not illuminate each other, what are the set of points? What can we say about the set of points that arise when you try to connect them? Do they always hit some finite set of points, and what are those points? And so on and so forth. So lots of open questions now sort of being studied with this new, very strong tool, and lots of progress being made in that direction. And let me also mention another problem and another kind of set of problems which you can attack using this. So amazingly enough, if you have a rational polygon, a general polygon, I should say, not necessarily rational, it's not even known whether there's a periodic trajectory on it. So it's not even known whether every triangle has a periodic billiard path on it. And on the other hand, for rational polygons, they always exist in a dense set of directions, and you can actually count them. And so here's a kind of a very central question in the field of rational billiards, is what it's called. So is it true that for any polygon P, rational polygon P, take the limit as t goes to infinity of 1 over t squared, the number of periodic trajectories, periodic billiard trajectories in P, of length at most t. And is it true that this always exists, this limit always exists? So in other words, what we're saying is a very, very refined statement about these periodic billiard trajectories on rational polygons. For irrational polygons, we don't even know if one exists. For rational polygons, we're asking if precisely the number of guys which do exist grows like some constant, which would be this limit, times t squared as t grows to infinity. And there's been lots and lots of progress on that, starting with work of Mazur. So Howie Mazur proved that this quantity has positive limb sup and finite limb sup and positive limb inf. In other words, this quantity is fluctuating between two positive numbers for any translation surface or any polygon, any rational polygon. And there's been more and more work suggesting that this might very well be true. Let me show you a slide sort of explaining what it is we're looking at. So here's a particular case. Ooh. Okay, so this grayish blob thing is what you get if you start with a very, very particular polygon. It's an L-shaped polygon where this side has length 1. This side has length phi, the golden mean. And similarly over here, this is 1, this is phi. And you play billiards in this polygon. If you play billiards in this polygon, whenever you see a periodic trajectory, you close up the periodic trajectory, and there's a distance that you've traveled that defines a vector in the plane, and you can just plot all those vectors in the plane. So the origin is in there, and all those dots represent periodic billiard trajectories. And you're seeing a very, very regular picture. So for this example, it was proved by Veach that this statement does hold. Such a limit does exist. There is a quadratic growth to these, in this particular rational polygon, but the method of Veitch used very extensively specific properties of this particular polygon. So if you find a periodic billiard path, you develop it in the plane, which means starting over here, instead of reflecting, I get a parallel line, what it would look like in the unfolding before reattaching to itself. And so it has an initial point and a terminal point, and you draw it on the plane. And so you're seeing lots and lots and lots of periodic billiard trajectories with very regular growth. And I guess I could call this a conjecture by now. The conjecture is that always happens for translation surfaces, for billiards in rational polygons. And it's very far from true for billiards in irrational polygons. And so I guess Pat Hooper proved that you could have growth which is much bigger than, I hope I'm saying this correctly, than quadratic. And as I said, it's not even known that this number could, for all we know, could be 0 in some examples for irrational polygons. For rational polygons, we're expecting this very, very detailed quadratic growth. And that's what Eskin, Mirzakhani, and Mohammadi were able to do using their theorem, is to actually prove this with an additional Cesaro average. So if you take this quantity and you average it again over t, then it converges. But this statement remains open. There is it's so-called Veitch surface, which means, in fact, it's Veitch's original Veitch surface. So if you go to a place where they serve Veitch surfaces, this is the original Veitch surface found by Veitch, which, or kind of a variant of it, which has the property that its stabilizer, so there's this GL2R action, it has a very rich group of affine symmetries, which means that its stabilizer in this action is actually a lattice in SL2R. And that's a kind of a very rare property. Typically, orbits have no stabilizers or trivial stabilizers. This particular guy has a large group of stabilizers, and that's what makes the thing possible.
Any conjecture about temperature?
Yeah, I think there are almost everywhere. Okay, it's not in the literature, but I think there are conjectures in people's minds or in grant proposals. I don't think there's a conjecture in print about the rate, but there should be a rate associated with this, which should follow from like spectral gap estimates and so on. So there's kind of a machinery sort of gradually being put in place to also get rates.
Each surface is a closed?
Pardon?
That surface there?
Yeah.
Closed.
No. This is a genus 2 surface. If you unfold it, you get a genus 2 surface in the same stratum as my second picture. So this is in H2. It's okay. Okay, so that's what I wanted to say about why one would care about these classification problems. You get a lot of information about these very kind of innocent-looking, I would say, elementary questions in geometry can be solved using these dynamics. And it sounds unrelated when you first see it, but if you think about it again, think about this illumination problem, this Tokarsky question first, maybe it's easy to explain for that. And you might ask, what is the relationship of dynamics to these questions in geometry? You might also ask, why isn't this moving? I can't show you. Oh, here we go. Okay, so let's take another look at this Tokarsky example. So how on earth would you relate the question of whether you can attach a billiard trajectory to connect these 2 points up by billiard trajectories? Well, the idea here is that, first of all, you can unfold, and you're actually looking at a translation surface with 2 points on it that you might be able to connect by a straight line. And then you start thinking about the set of pairs of points on translation surfaces which cannot be connected by straight lines in that geometry. And it's not hard to show that that's a GL2R invariant closed set. And since we have a classification or almost classification of GL2R invariant closed sets, we can start attacking this kind of a problem. Similar story for the, similar but more complicated story for this problem of counting billiard paths. Now, what I want to talk about today is the work that we've been doing on extending this, all this work that's been done for the full GL2R action to our favorite flow, which is this Horocycle flow. So we're asking whether we can prove similar results for the Horocycle flow. That's the question that we're focused on. If you believe that the analogy with Ratner's work in homogeneous dynamics should serve as a guide, then you might be tempted to believe that this can be done or that this is true, because this group, this is a unipotent group, so it satisfies the assumptions that Ratner assumed. And what I want to report on today is some good news and some bad news in this direction. Well, so I'm pretty safe saying there's good news and bad news, because I'm not saying what's the good news and what's the bad news. So it sort of depends on whether you believe that one can extend this or whether you believe that it's not possible to extend this. So we have pieces of evidence sort of going both ways. And so one piece of news is that for general strata, we're able to come up with examples that are stranger than come up in the GL2R action case. Okay, so we get one set of results that we have has to do with measures and orbit closures with unexpected features. And the other set of results that we have say that, in fact, one can extend these results to the Horocycle flow in some subsets of translation surfaces with additional hypotheses. So in some restricted settings, it is possible to make this extension. So let me very briefly talk about this set without writing anything down and focus on the other part. So what we can exhibit are measures and ergodic measures for the Horocycle flow, and therefore orbit closures, such that the support of the measures, first of all, has a boundary. So all of the measures that come up in the Eskin, Mirzakhani, Mohammadi picture are supported on nice manifolds, and we get this additional features that these manifolds might have boundary. We also get the supports of the measures as being objects which have an infinitely generated fundamental group. So all the objects that come up in EMM in this work do not have that feature. They have a nice topology, in a sense. And another thing that comes up is that the Eskin, Mirzakhani, Mohammadi examples are flat. They're flat. The coordinate systems on these strata that I've described don't only make it into an orbifold, they make it into an orbifold with an affine structure. And all the things that come up in the GL2R classification are all flat manifolds in this structure, but for the Horocycle flow, we're able to exhibit orbit closures which are not flat in that sense. So we're seeing a richer picture, a more complicated picture for the Horocycle flow in general. And the other piece of news that I want to talk about today has to do with classification in restricted settings. So,
if you have one of those examples with this infinitely generated fundamental group for U, and then you take its G orbit, is it one of the ones that's dense in the whole?
Yeah, it's going to be bigger. So in some examples, it'll be one of the ones that it's one of the ones that it's going to be one of the ones that's the examples that we have. It's not going to be dense, but it's going to be in a bigger orbit closure, which was already studied by McMullen. So these actually already come up in genus 2, and the orbit closure is going to be bigger. The boundary and the infinite fundamental group, or infinitely generated fundamental group, are going to go away, and there's going to be a nicer manifold.
But it might get some restricted.
It will be, in this particular example, it will be not a generic surface. But presumably this comes up. We believe that this comes up quite generally. So I was about to write, so we get classification of measures, orbits, plus equidistribution in restricted settings. So I'm going to try to state some results and make some definitions and give you the flavor of this. So we're studying a particular locus in genus 2 in the stratum H11. So we're studying the U action on so-called eigenform locus, eigenform loci in H11. So what does this mean? So as I told you earlier, McMullen classified the SL2R or GL2R invariant measures and orbit closures in this stratum H11. H11 is one of the genus. There are two genus 2 strata. H11 is one of them, and he has a classification. In his classification result, there are three cases. There are the dense orbits. There are the closed orbits. The closed orbits are these Veitch surfaces that I described a few minutes ago. And there's an intermediate case where the orbit is not closed and it's not dense. And this intermediate case lies in some submanifold. Now, H11 is 7-dimensional. We're always talking about area 1 surfaces. So H11 is a 7-dimensional manifold. And inside it, there are countably many 5-dimensional closed manifolds. And these are called the eigenform loci. So there are countably many five-dimensional SL2R invariant closed sets in H11. McMullen so they were first discovered by Carrie-Anne Calta, who was a student of Alex Eskin as part of her thesis, and she described them in one form, and McMullen described them using an algebraic geometric description, and he was the one who coined this name, the eigenform loci. So in the McMullen language, these are surfaces in genus 2 whose Jacobian has an abnormally large ring of endomorphisms, and the one forms are eigenforms for this ring of endomorphisms. So that's why they get called eigenform surfaces. So let me just write that down sort of sketchily. So they are eigenforms for the ring of endomorph. So omega, so x omega, such that omega is an eigenform for the ring of endomorphisms of the Jacobian of x. And the Jacobian of x is strictly larger than it should be, which I guess is z. So these Jacobians always have endomorphisms which are multiplying by scalars. And if they're strictly larger, then if the ring of endomorphisms is strictly bigger than this, then they have an abnormally large ring of endomorphisms. And that's the property of x that's relevant. And on x, you want to put a holomorphic 1 form, which is a simultaneous eigenvector for this action. That's McMullen's description. There's going to be another description that I hope to get to in a few seconds. But that's where we're looking. We're looking at a very special subset that comes up in this classification in genus 2. But it's still a 5-dimensional space on which we have a 1-parameter action. So it's still challenging to make a classification result. And I should also say for the experts that this is not going to be, hopefully, the end of the story. So there's a whole bunch of invariant loci in arbitrary strata, which are now called the rank 1 loci. They've been described very nicely and very abstractly by Alex Wright, who's a former graduate student of Eskin. And in Wright's language, we're actually looking at the so-called rank 1 loci. So it's quite likely that things that we're doing in this particular setting all do extend to the greater generality of rank 1 loci. And I'll tell you a little bit about rank 1 loci in a second. But let me first state some theorems. So there are countably many of these guys. They're indexed by a number d, which tells us, an integer number d, which tells us what this ring is. And so what do we prove? And so we classify all the invariant measures and they come in 7 families. We classify all orbit closures and we see that any orbit for this U action is equidistributed in the support of one of the measures that I discussed. So and let me just write additional equidistribution results, which I hope to have time to tell you more about. So if you've not studied Ratner, I should say a few words about the kind of information that you get. This is very analogous to what Ratner did. So on a general, so this is a flow on a space. So in general, of course, you don't expect to have a list of the measures. But let's talk about the orbits for a while. The orbits may be dense in some subsets. We're telling you that they're always dense in supports of these measures. Not only that, if you average along these orbits, every single orbit is going to be generic, which means that it averages correctly to one of these measures. So typically in dynamical systems, you might have orbits which sort of spend some of their life behaving as if they were governed by one measure, and another part of the life depending as if they were, pretending they were being influenced by another measure, and so on and so forth. This never happens for these flows. Okay? Okay, that's essentially the theorem. To explain how the theorem, so I'm going to quickly explain how the theorem works. So I have until 40 past, right? So I'll explain how this theorem works, and along the way I'll give you more information about what this eigenform locus is like and what the rank 1 loci of right look like. And so to understand this, we first have to look for invariants of the Horocycle. And as you're seeing, there are many more cases here than come up in the SL2R classification. So the SL2R classification of McMullen says that in this locus, either every orbit is dense or it's a Veitch surface. So it's a closed SL2R orbit. There are only 2 cases, and we're seeing 7 cases. And so the These cases are distinguished by some invariants. Let me describe those invariants. So the first invariant is the horizontal saddle connections. So if you have a horizontal saddle connections are an invariant for the U action. Let's go back to the picture. Hope it'll come up in a second. So this is the picture that I showed when I was describing the Horocycle flow initially. So let's take a look at the horizontal line joining the wide part of this translation surface. That's a horizontal line. And that is a saddle connection. You can ignore the black dots that are on it. But just think of it as a line joining the singular point to itself along the center of the picture. Now, when you apply the shear, it's a horizontal shear. It preserves the horizontal line. So no matter how you shear, that horizontal line is still going to be there. So the existence of a horizontal saddle connection is an invariant. And so what we do is we organize the topology, and its length is also an invariant. We organize the topology of these things, this horizontal piece of data in a diagram. So we call these horizontal data diagrams. So in our situation, we have two singular points, and we could potentially have three different horizontal saddle connections. There's plenty of different ways they could connect those singular points. That's what you're seeing on the top picture, the four different ways. And then we could have like a partial collection of horizontal data diagrams. So you have to start with that as your first invariant. Your second invariant involves what we call the rel motion or the rel foliation. So let me describe that. And so here is a surgery that you can do on translation surfaces that have two singular points. So what's the difference between the left-hand picture and the right-hand picture? These are translation surfaces with two singular points, and the empty dots and the black dots represent different singular points. I'm keeping the black dots in place, and I'm moving all the white dots to the right a fixed amount relative to the black dots. That's the difference between the picture on the left and the picture on the right. One has been sort of sheared in a strange way. It's called rel because I'm only affecting relative periods in the, so these are only affecting basically integrals on paths connecting distinct singular points but not closed curves. So it's not affecting absolute homology, only relative homology, and that's the definition of this action. Now, since we're moving in a horizontal direction, this action commutes with the Horocycle flow. I mean, that's not completely a theorem, but it should be intuitively clear. You're moving horizontally, and then you're applying the Horocycle flow is the same as first applying the Horocycle flow, then moving horizontally, because the Horocycle flow doesn't touch the horizontal direction at all. And there's a possibility that this naively defined surgery will go bad if you keep going. So after a while, you get a polygon with these screwy self-crossings, and you don't know what to do with it. But everything is only defined up to cut and paste equivalence. So now if you see this, you would cut up and rearrange the surface, and hopefully you could keep going. And in some cases, you can keep going, and then in other cases, you cannot keep going. So the invariant is how far can you push? How far can you push along the rel direction? That's an invariant. And a third invariant is, does this rel motion preserve the measure that you're interested in? These are two new invariants that we have for these Horocycle invariant measures. So let me skip ahead because I'm short on time, and just let me show you how do I do this? I want to show you basically what our measure classification looks like. So our measure classification follows earlier work of Calta and Wortman, and we are describing these 7 families of measures in terms of 2 pieces of data. The one in the middle here is the horizontal data diagram that I described. The one on the right is the invariance group inside a bigger group. it's bigger than SL2R, it contains this rel operation as well. And essentially, all the cases are distinguished by these invariants. If you look carefully, you'll see that some places, some additional invariants need to be put in place. But those describe the different cases that show up. And let me just say a final word about, so let me just give an example. Maybe case number 2 is you take a Veitch surface, you push it by its SL2R orbit. That's a closed orbit. It has a nice SL2R invariant measure on it. Now push surfaces in that orbit by this rel operation to some fixed distance. You get a shifted object, which we call the shifted G-orbit. And that guy is Horocycle invariant, and that appears on our list. And just the final thing that I wanted to say, I wrote down that we have equidistribution results. Let me just tell you an idea of what that might look like. Take this shifted G-orbit, as in case 2, and just keep pushing it further and further along using this rel operation. Where does it go in the limit? That's a question you might ask. And the answer is that it gets equidistributed in a bigger space. And we analyze exactly what can happen to each one of these measures. So these measures sort of come with a parameter of push. And we analyze exactly what happens in all possible pushes. Where do these measures go? And what are they equidistributed on? And always sort of, all these objects always like to equidistribute on nice manifolds. OK, I'm out of time, so I'll stop here.
Questions?
Yeah, so what it's measure description. So could you take one of these lines? Then exactly what it means.
Yeah, OK, so suppose I give you a translation surface. And you want to know where does it go under the Horocycle flow. So then I tell you, well, first look in this column and check how many horizontal saddle connections does it have and what do they look like. So if they, if I start moving this, it will take time. So if they have a full, as big as possible, a set of, as big as possible, a set of horizontal saddle connections, then you'll be at the bottom in cases 6 and 7. And we're telling you that it's either a closed horocycle that you're on or a minimal set for the Horocycle flow, which is a 2-dimensional torus sitting inside this space. Now suppose it's not empty and not full, so it's either case 4, 5, or 5. There's 3 cases in the middle. Well, then I will tell you, look at the complementary. So let's just, there's a distinction between 4 and 5. Again, we have a partial diagram. In case 4, it consists of 1 horizontal saddle connection. In case 5, it's 2. It's a description of every surface on the support. Every surface on the support comes from taking 2 tori, sticking in a horizontal slit, and gluing them.
Other questions?
Yeah.
So where does this use the EMM classification?
It doesn't use EMM.
Assuming that you know the strata, then you can.
So this we didn't use in this situation. Well, we used. I shouldn't say we didn't use EMM at all. We used EMM at one step, but I probably could avoid using EMM. But this is, in some sense, using. Okay, let me take that back. We do use EMM. We use Eskin, Markloff, Morris. We don't use Eskin, Mirzakhani, Mohammadi. So there's an Eskin, Markloff, Morris paper that came out about 10 years ago, in which what they're doing is they're looking at the original Ratner argument for Horocycle flows. The original Ratner argument is basically you're taking 2 nearby Horocycle trajectories, and you're pushing them forward, and you're comparing how they deviate from each other. And in these rank 1 loci, or in this eigenform loci, there's a nice set of parameters, and you can really describe how they shear away from each other. And that's most of what we do. There is a particular step which is made quicker by using another result of Eskin, Mirzakhani, Mohammadi. So we also do that. But in some sense, the type of arguments that we're using were around before Eskin, Mirzakhani, and Mohammadi. They're very close to Ratner's original arguments.
So that means that there are results like this that you can already do in a higher genus case?
Yeah, so we expect to be able to do, so this is a very detailed list in a sense. So we need to know lots of information about what kinds of saddle connection configurations can arise in this particular stratum and so on. So that's been worked out in a lot of detail in genus 2 by Matt Bainbridge, Kurt McMullen, a bunch of people. And if we don't have all that information in some higher genus, we will still be able to tell you something like all the invariant measures, there are countably many of them. Countably many families. These come in families. As you see, there's a push involved. The push is a real parameter. So there are countably many families. Typically, there should only be finitely many families. And the measures are coming from pushing each other along using rel operations and things. General statements like that can be made in much greater generality. The advantage of genus 2 is that you can really write down the full list.
Okay, so let's thank Barak again.